Hello once again, and a very warm welcome to you. We are going to be continuing on this course, Data Communications and Networks. My name is Dr. Zulfikar Kassam. Thank you for joining once again. Today we'll be talking about data and signals. This is section 3. We are starting a new section this time around. Section 3, we have the other lectures already posted. So this is a new section 3 where we're going to be focusing on data and signals. So in terms of data and signals, for data to be transmitted across a communication medium, it must first be converted into a signal. Now, depending on the medium, this signal may take a different form. This could be electrical signals transmitted over copper wires. It could be electromagnetic signals, such as radio waves or microwave, transmitted wirelessly through the air. For example, obviously the wireless access points use radio waves, and if you are talking or communicating to satellites, they'll be using microwaves. Then these optical signals, light pulses transmitted through fiber optic cable, if that's what you have. So this transformation ensures that digital or analog data can travel efficiently across physical channels at the physical layer of the OSI model. One of the major functions of the physical layer is to move data in the form of electrical signals, electromagnetic signals, or optical signals across a transmission medium. Now, this data and signals can be analog in nature or could be digital in nature. So, analog data refers to the information that is continuously changing, and digital data refers to information that has discrete states or discrete values. So analog data tends to be taking on continuous values, as we mentioned, and digital data has discrete values. If we look at the analog signal, it has a changing wave signal. Now, this could be varying in amplitude at times, could be varying in frequency at times, could be varying in phases as well. Okay. So if we look at analog data takes on continuous values. Example is the sounds made by a human voice. When a human speaks, an analog wave is created in the air. Now, sound can be captured by a microphone and converted to an analog signal, or sampled and converted to a digital signal. Radio waves, microwaves, infrared, visible light are also forms of the analog signal. They vary continuously in amplitude, frequency, and phase. So we'll be talking later on about amplitude, frequency, and phase, but for this moment in time, we need to understand that these are the different parameters that comprise or constitutes the analog signal. Now, a digital signal will look something like this. So a digital signal is a signal that represents data as a sequence of discrete values of zeros and ones. So it'll basically have two different values, right? Now, there are digital signals which will have multiple states. It may not just be 0 and 1. There could be multiple states in which you can carve out more information, but there'll be discrete values nevertheless. But instead of having just two values, it could have 4 different values, but they'll still be discrete in nature. And we will talk about that in a later lecture. Okay, for now, to make things simple, let's assume it only has two different values. So digital signal, as we just mentioned, takes on discrete values. For example, data that is stored in the computer memory is in the form of zeros and ones. It's binary in nature. It's either a 0 or it is a 1. Digital data can be converted to a digital signal and then transmitted, or it can be modulated into an analog signal for transmission across a medium. And we will see how a digital signal in certain cases may be changed into an analog signal before transmission and then reconverted back to a digital signal at the other end. So in data communications, we commonly use a periodic analog signal. And sometimes it could be non-periodic analog signal as well. Periodic signals can be classified as simple or composite in nature. A simple periodic analog signal is a sine wave. A sine wave is the simplest form of a wave that cannot be decomposed into simpler signals. So that's the simplest form, the sine wave. A composite signal, on the other hand, a composite periodic signal specifically, is composed of multiple sine waves. So let's look at the sine wave. It's the simplest form of a wave, which is very simple in nature, right? That you may have seen, very periodic in nature and very simple as well. So a sine wave is basically the most fundamental form of a periodic analog signal. When we visualize it as a simple oscillating curve, its change over the course of a cycle is smooth and consistent. In short, a sine wave is periodic in nature and continuous. Each cycle consists of a single arc above the time axis followed by a single arc below the time axis. And a sine wave can be represented by three parameters. There'll be the peak amplitude, which is the displacement from the zero value, the frequency, the number of cycles per second, and the phase, how it is being transformed from its center starting point. These three parameters fully describe a sine wave. So now let's look at the sine wave with different frequencies. We have on the top here a sine wave that completes 12 cycles within the 1 second period. So within 1 second, it completes 12 cycles. The number of cycles a sine wave completes is known as the frequency. Number of cycles it completes in 1 second is what is referred to as the frequency of the wave. So in short, we can say the frequency refers to the number of periods or the number of cycles that it completes in 1 second. So you see in the 1 second period here, it has completed 12 cycles. So basically the frequency is equal to 12 hertz because it has completed 12 cycles in 1 second. On the other hand, we have another scenario in which the number of cycles in 1 second completed is 6, right? So we can see the frequency of this wave here is 6 hertz because it completed 6 cycles within 1 second. Okay. Now T is the time period that it takes to complete that cycle. So you can see T over here. This is also the time period is much shorter here because the wave is smaller. While here is the time period to complete one wave is twice as large as it is over here. We'll talk about that in just a moment. For now, we need to understand that there is a frequency of a wave, which is the number of cycles that it completes in 1 second. Then there is the amplitude. That's the other parameter of a wave that we need to understand. The peak amplitude is the maximum displacement it has from the center point, right? So the peak amplitude is right here of this specific wave. A signal with high peak amplitude is shown in here. And then we see a signal with a much lower peak amplitude. This is the strength of the wave, basically. So the peak amplitude of a signal is the absolute value of the highest intensity proportional to the energy that it carries. For electrical signals, peak amplitude is normally measured in volts. The power in your house, for example, can be represented by a sine wave with a peak amplitude of 155 to 170 volts. Now, these are not the numbers that you are used to hearing because we don't talk about power in the house in terms of the amplitude, right? Because it's common knowledge that voltage of the power in Canada and US homes is quoted in root mean square value. It is not quoted in peak amplitude, it's quoted root mean square value, which is 110 to 120 volts. So that's in North America, we have 110 to 120 volts. If you're in England and many other parts of the world, you may have 220 to 240 volts. But that is the root mean square value, not the amplitude. Okay. The way the root mean square value is calculated is done by dividing the amplitude divided by the square root of 2, which is 1.4142. So basically, root mean square voltage of an alternating voltage represents the DC voltage that dissipates the same amount of power as the average power dissipated by the alternating voltage, right? So when we talk about the root mean square value of an alternating voltage, it represents the DC, the direct current, which is a kind of straight wave that we are used to seeing in DC voltages that dissipates the same amount of power as the average power dissipated by the alternating voltage. So for sinusoidal oscillation, the root mean square value equals the peak value divided by the square root of 2, which is, as I mentioned, 1.4142. If you divide 170, which is the peak voltage, by this value, which is square root of 2, this will give you 120 volts, and sometimes you'll see 155 divided by square root of 2 is equal to 110 volts. So basically in the North America, this is the voltage you will experience. As I mentioned, if you are in England or other parts of the world, most parts of the world do use 220 to 240 volts. Now, when we talk about the wavelength, okay, the wavelength is the length of one complete cycle of a wave. So you can measure this basically from crest to crest here, right? Which is the peak to peak or crest to crest. This is the wave crest, as you can see. There's a wave trough as well. If you do the same thing over here, you'll get exactly the same result. So the wavelength is basically the length from one peak to the other peak, or one crest to the other crest. So wavelength is length of one complete cycle of a wave. In terms of waveform, the wavelength is typically associated with waveforms such as electromagnetic waves, like light, radio waves, sound waves, water waves, and any other type of periodic wave. The crest and trough, you saw that in the previous slide. In a waveform like a sine wave, the wavelength is measured from one crest, the highest point of the wave that we saw, to the next crest, or from one trough, the lowest point of the wave, to the next trough. It represents the distance the wave travels during one complete oscillation. In terms of the scientific notation, the symbol used to represent wavelength in Greek letter lambda. The units of wavelength is expressed in meters, could be millimeters, nanometers, depending on the length of the wave, or the appropriate length units depending on the scale of the wave. For example, visible light has a wavelength in the range of 400 nanometers, which is the violet color, right, to 700 nanometers, which is the red, which has a larger wavelength. The red has a larger wavelength here. Violet has a smaller wavelength of 400 nanometers. Now, wavelength is related to frequency, right? So wavelength and frequency are actually inversely related. This means the wavelength of a wave increases as its frequency decreases and vice versa. So the relationship is described by the wave equation, which is C is equal to lambda times nu. Okay, this looks like a V, it's actually a nu. So c is the speed of light, okay, or the speed of the wave in the medium, basically more or less a vacuum, right? 3 times 10 to the 8 meters per second. Lambda is the wavelength in meters, and nu is the frequency in hertz. And sometimes the frequency is written as the letter F instead of nu, so you'll see some documentation in which it will say C is equal to lambda times F versus nu. So this equation holds true for electromagnetic waves like light, where the speed of light is a constant value of 3 times 10 to the 8 meters per second. Okay. So the speed of radio waves in a vacuum, such as outer space, is approximately the same as the speed of light, which is about 299,792,458 meters per second. So approximately 300,000 kilometers per second, or 186,282 miles per second. In other mediums, such as air or through materials, the speed of radio waves can be slightly slower than the speed of light, depending on the properties of the medium. So the speed of radio waves in specific medium is determined by the materials, what is called the refractive index, which is a measure of how much the speed of light is reduced when it passes through that material. If you have optical fiber, for example, it could be very, very close to what you see in here. If it is very, very pure fiber, you may see something very, very close. But sometimes, depending on the refractive index, it could slow down to some degree. Okay, so we looked at the notion of frequencies. We saw a similar wave before in one of the slides in which we said we completed 12 cycles within 1 second. So the frequency is equal to 12 hertz. The period is the time it takes for the wave to complete 1 cycle. So the period refers to the amount of time in seconds a signal needs to complete 1 cycle. So you can see here the period is 1/12 of a second to complete 1 cycle. If you look at this other wave in which the frequency is 6 hertz, so 6 cycles per second, which is the frequency, the period of this wave is 1/6 of a second. Basically, it takes 1/6 of a second to complete 1 full wave cycle. All right. So we'll speak about the period in the next slide, and we will do some examples next time around. Okay. So the period T refers to the amount of time in seconds a signal needs to complete 1 cycle, as we saw in the previous slide, while the frequency refers to the number of periods, basically the number of complete cycles in 1 second. Note that period and frequency are just one characteristic defined in 2 different ways. So period is the inverse of frequency, and frequency is the inverse of period, as the following formula shows. So the frequency is equal to 1 divided by the period of the wave. Conversely, the period of the wave is equal to 1 divided by the frequency. So thank you for watching. I hope you enjoyed this lecture, and we'll continue on next time. Take care. Have a good day.